So we'll start with a talk by Andrew Lee. He'll be talking about variations on a theme of Morse. Go ahead and tell people how you want them to ask questions during the talk.
Yeah, I think feel free to just chime in the middle if you have any questions. Um, yeah, so the title of my talk is Variations on a Theme of Morse. And so the kind of subject of my talk is a field called Morse theory, which is ubiquitous in modern geometry and topology. It's what I study. And the kind of origins, I guess, of Morse theory are really in this field of what is called calculations of variations. And so my talk is going to be kind of building this bridge between calculus of variations and Morse theory, but kind of in the reverse order. So I'm going to start with Morse theory, and then kind of go back towards the historical, I guess, precedents, which is the calculus of variations. So I want to talk by starting about spheres. So this is going to be like I guess, a little warm up. So okay, just as a reminder, the n-dimensional sphere is going to be defined as the points x in Rn plus 1, such that the norm is x1 squared. This is equal to 1. So this is the kind of standard distance from the origin. I'm writing it squared because I don't want to know what square root. But so if for n equals 1 and for n equals 2, it's kind of easy to visualize what's going on here. So n equals 1, we have the standard circle. N equals 2, we have the standard sphere. Um, and but then for n equals 3 and higher, we kind of run into trouble, right? Because in case of n equals 1, we have an ambient two-dimensional space. In the case of n equals 2, we have an ambient three-dimensional space. But in the case of n equals 3 and above, we need to have an kind of 3 plus 1 dimensional ambient space, a 4-dimensional ambient space. And so it's a little bit trickier to understand what's going on. So instead of trying to kind of visualize higher dimensions directly, I'm going to kind of take the strategy of splitting into kind of lower dimensional objects. So I want to demonstrate this by looking at the sphere. So let's say I have this, the two-dimensional sphere. So I'm in 2 dimensions, and let's look at this function f, which is defined as f of x is equal to x3. So what that means is that I have the x1, x2, and x3 coordinates. And I just, whenever I have a point on the sphere, I project it onto its height. And so this is kind of what I'm going to call a height function, going from S2 to R3, sorry, R. And we can look at what are called the level sets and the sub-level sets of this function. And so one time I heard this talk where the speaker was pontificating about climate change, and he said, "Oh, this is going to be a very applicable analogy to people in this generation, because imagine you have like the sea, and the sea is at some level, I guess C, um, and then you look at everything that is at or below kind of this height C. So this is what you call the sub-level set. So we have the sub-level set, which I'm going to denote in this notation as the preimage of this closed interval, which is the points in S2 such that f of x is less than or equal to C. And then, of course, the cusp of this, or like the kind of stuff that's at the surface, is going to be the level set. So I'm just going to denote this like that. S2 for f of x is equal to C. Okay, perfect. So, okay, what does this allow us to do? It allows us to like cut up our function, or sorry, our space into its kind of level sets. So if we start at the level set of -1, at -1 we have like just a point, And then as we go up, we should have like bigger and bigger circles. And then this is at 0 where I have a circle of radius 1. And then as I continue scanning back up, then my circle's going to get smaller. And then I get back to a point at the top. And so this gives us a way of kind of like taking our two-dimensional thing, slicing it into one-dimensional slices, and then saying, okay, if I know how to glue these one-dimensional slices together, then maybe I have a chance of recovering kind of an understanding of the structure of this overall two-dimensional thing. And so this can actually kind of help us think about S3. So S3, I don't really know how to visualize this, but I can still write down the same kind of function. So in this situation, instead of x3, I'm going to take x4, the kind of the fourth coordinate. And I have the same function to r. Now I can't do the same thing where I can kind of draw S3 and S and R4 because I can't visualize R4. But nevertheless, I can do a similar thing as I did here on the right of like looking at level sets. And so similarly at -1, I start with a point. And then as I get a little higher, I actually end up with like these small spheres. And then I'm drawing them a little oblong because I can't really fit them all. But still bear with me. The idea here is that at -1 and +1, I only have kind of the north and south poles with respect to the x4 axis. And then as soon as I get a little bit inside that interval, say like 0.9, then I get like a sphere of a very small radius, and that radius goes up to 1 as I get to 0, and then falls back down to 0 as I scan all the way up to +1. And so hopefully this gives you a sense if you kind of, you can also imagine like kind of a movie that plays where it starts as a point of the origin, and then it slowly expands to the sphere of radius 1, and then slowly expands back to a point as you kind of move the t coordinate, which we can think of as the fourth dimension. But anyways, this kind of process allows us to try to visualize things that are higher dimensional than what we can kind of physically draw. Cool. So this is kind of the first kind of warm-up / example. But the real kind of meaty example here is the example of a height function on the torus. So I'm going to draw a picture here. We have a torus. This is a kind of the surface of a donut. And I'm looking at the function which returns the height. And so implicitly what I'm doing is I have all of this inside of R3. So this is the torus inside R3. I'm writing the torus as T2 because it's two-dimensional. I have n-dimensional generalizations if I want to. So yeah, again, I take a point and then I just map it to its height, right like that. So, okay, the observation that I want to make is that if I look at, let's say that, just to make our lives simple, let's say these points map to 0, 1, 2, and 3. And let's look at the sublevel sets at and between these points. So below 0, I have nothing. And then at 0, I have kind of just 1 point. But then you'll notice that between 0 and 1, I have a kind of like cup looking situation. But no matter where I am between 0 and 1, everything should look like a little cup. It's only when I pass 1 that I end up with something that kind of resembles like maybe like a piece of macaroni or something like that. As the kind of the lip of the cup cinches and then like kind of kisses itself. And then as I scan up between 1 and 2, then I'll have this kind of proper elbow of macaroni. But again, no matter which number I pick between 1 and 2, I should end up with a sublevel set that looks essentially the same. And then when I go above 2, I'll end up kind of pushing these kind of two open ends together. And so I end up with something that looks like this, perhaps. And then this is at 2. This is between 2 and 1, 1 and 0. And then between 2 and 3, these two kind of holds have merged into one so that I have something that looks like this. And then finally at 3, I have the full torus again. And so the kind of critical observation to make here is that the topology, kind of the deformation invariant structure of this space only changes when my number C crosses over these 4 points. And these 4 points, these 4 special points, these are going to be what are called the critical points. Cool. So hopefully many of you have seen calculus, at least in the single variable context. I'll be talking a little bit about multivariable calculus. Many things kind of are similar in this setting. But okay, so I'll talk a little about what I mean by a critical point. So there's kind of 2 different ways of thinking about critical points. I have a question. Yeah, I'm just about to talk about that. So hang tight and I'll continue talking about how to define these critical points. So, okay, there's kind of method 1. So if I have, I'm going to kind of go back to the general setting. If I have a function g from Rn to R, so this is an n variable function, then, and if I pick a point in Rn, then its gradient, so its gradient, oops, is this guy, which is the kind of vector of partial derivatives at that point. And the kind of, I guess, intuition for this is it's the direction of fastest ascent. But then the standard way of thinking about critical points is a point where this gradient vanishes. And so this should kind of rhyme with the standard thing in single variable calculus, where you're looking at critical points or points where the kind of first derivative vanishes. This is the replacement of the first derivative in the multivariable context. Okay, but remember, like we were looking at a function from the torus to R, not from Rn to R. And so there's a little bit of a subtlety here that we have to kind of fix. And so actually in this setting, we want to consider like f as a function restricted to the torus. And yes, it's defined on the full space, but I want to consider only restricted to the torus. And so what I do is if I look at a point here, let's call this point x, I can look at its tangent space, which you can kind of think of as the plane which most well approximates the torus at that point. And let's say that I figure out what the gradient is. It looks something like this, like that. The kind of gradient of the height function should be kind of just the unit vector pointing upwards. But then what I need to do is like restrict it to the torus. And so what I do is actually kind of project it down so that it's inside of this this space, this tangent space. So this guy over here, this is what I actually call the gradient of f at x. So this is maybe sometimes what I would call the ambient gradient. And this is the kind of restricted or tangential gradient. Cool. And then so, okay, now that I have this terminology in place, again, a critical point is just a point where the gradient vanishes. And so in our case of the torus, it's a point where the upward pointing vector. So here, remember our height function is x3. And so the kind of ambient gradient is just going to be 0, 0, 1. So it's the kind of constant vector pointing upwards. So then this question comes down kind of like what is the tangent plane at each point? And if the tangent plane is parallel to the xy plane or the x1, x2 plane, then it has to be a critical point. So that's the kind of first way of thinking about critical points. But I have a second way of thinking about critical points that I want to consider. So remember, let's go back now to a function from Rn to R, and x is a point, and v is a vector. We have the directional derivative, which is this little object. I'm going to define it as the derivative of, x plus tv, g of x plus tv evaluated at t equals 0. And then in this context, x is a critical point if dvg is equal to 0 for all v in Rn. And so, okay, now we have to, again, do this. If we want to return to the torus, we have to do this restricting kind of situation. But hopefully maybe it's a little bit clear what this restriction should be. If I have f from, let's say, t2 to r, this is our, oopsies, that's terrible. Our example earlier. Recall we only really care about the directions in this tangent space. And so what I'll say is that x is a critical point if the directional derivative of f at x is equal to 0 for all v only in the tangent space at x. So these two kind of ways of thinking about the critical point turn out to be equivalent because of the kind of standard formula that you have relating the directional derivative to the gradient, which is if you denote this the Euclidean inner product or the dot product, then I have this equation that the directional derivative with respect to the direction v is equal to the dot product of the gradient of f at that point and v. And so, of course, if the gradient vanishes, then this left-hand side should vanish for all choices of v. And similarly, if the left-hand side vanishes for all choices of v, the only vector kind of satisfying that choice would be 0. And so this kind of equation, I'm harping on this because there's kind of a slight another version of this equation that'll come up later in my talk. I'm harping on this because this is kind of the central thing that allows us to think about critical points in two ways. Okay. Great. So the thing about Morse theory is that here in this case I picked a very specific function f. In general, you actually have a very, very wide amount of freedom to pick your function f and still have these nice properties where kind of the space is kind of stratified by these sublevel sets. But you can't always guarantee that, so you kind of have to pick what's called a Morse function, which is kind of a sufficiently nice function. But if f is a Morse function, then we can ensure that the transitions that happen along critical points are nice. And what I mean by that is I have kind of, for each n, I have kind of n possibilities. So I'm going to restrict to the case of n equals 2. The transitions have to look like locally, either like x squared plus y squared, x squared minus y squared, or x squared minus x squared minus y squared. So in this x squared plus y squared, I have this kind of parabolic cap situation. In this situation, I have a kind of saddle point. And in this situation, I have a kind of cap. And more generally, you have kind of every critical point locally looks like something of the form negative x1 squared minus x lambda squared plus x lambda plus 1 squared plus xn squared. And so you have kind of lambda negative parts and then n minus lambda positive parts. This lambda is what we call the index of the critical point. And so this here is an index zero critical point, 1 and 2. And so what this allows us to do is kind of like turn the understanding the problem of understanding the topology of a manifold into kind of understanding how you can kind of piece these Lego parts together. So to kind of finish off the example, I can think of the torus as having started up as a little cap, and then I add a saddle. Oops. And then another saddle, and then another cap. And then I kind of specify the way in which I glue them together such that I get the torus back. Cool. So I'll stop on the Morse theory now. There's a lot more to say about this, but for the purposes of the story, our kind of moral here should be that to understand our space X, we give it a Morse function F, and then look at critical points. So are there any questions at this stage? Cool. Okay. In that case, I'll move on. So, okay, the next part, I'm going to start talking about calculus of variations. So the calculus of variations starts off in these kind of classical physics problems. And here is one of the most kind of classical motivating problems. It's not on my I can't spell. Tato problem, which is that let's say I have a closed curve. I'm living inside R3, and I have a closed curve gamma. Simple, smooth, closed curve. Then I want to find a surface, we call it sigma, which has the boundary gamma. Then I can ask, when can I find a sigma that has minimal area? How do we pick which Morse function to use? The general answer is kind of, you can pick any Morse function and you get the same answer. The reason for this is actually very, very subtle, but feel free to ask about it at the end. Yeah. So, yeah, what I'm looking for is, can we find sigma, which minimizes area for given boundary gamma? So the physical context in which this comes up is in the geometry of soap films. So if you imagine gamma as like a kind of a piece of wire that you submerge into soapy water, and then you take it out, then the resulting geometry is the resulting geometry of the soap film should try to minimize area. Okay, so this seems like a very different problem than Morse theory, but if you remember, if you have a minimum of the area, then in particular you have a critical point of the area. And so actually, if you expand your kind of your thinking to not just minima but critical points of the area function, then we get into a context where we seem like we're doing Morse theory. So to be more specific, I'm looking at the collection of surfaces with boundary gamma, and I'm looking at the function area, which takes this and gives me a real number. And so in Morse theory, I allowed myself to pick kind of any Morse function as long as it's Morse, right? But here, like, I don't get to pick what area means, and so I'm kind of forced to use this very particular function. But that doesn't mean I'm completely lost. So for the sake of kind of simplifying the exposition, I'm going to restrict to a very specific case. So it's Rn, I'm going to have omega inside of Rn be an open set. You don't know what that means, don't worry about it. You can just think of like a ball. So it looks something like this. And then I have a function phi. So this is omega is kind of the inside, and I have this boundary, should denote del omega. I have a function phi, which determines my boundary conditions. So the graph of phi should look something like this. So this is kind of y equals phi of x. Okay, then I want to look at the set of functions u from omega to r, which agree on their boundary. So functions u, where when I take the graph, it looks maybe something like this. In this context, the area is actually pretty easy to write down explicitly. So I can write down, if I have area of the graph of u is equal to the integral over omega of the square root of 1 plus the gradient squared, all square root. And if you remember the kind of the formula for arc length in single variable calculus, this should seem kind of suspiciously similar. Of course, area is like a higher dimensional analog of length. But okay, now what's the critical point of the area? So it turns out that okay, so the first definition is going to be kind of confusing for us, right? Because if we try to think about the gradient of the area, we're going to kind of get lost because like this set S is like a really weird infinite dimensional set. But instead, we can still make sense of the directional derivative. So the directions I'm going to take are what are going to be called smooth, compactly supported functions. This is like a kind of fancy way of saying a little wiggle. And so I'm going to be considering functions that look kind of like this. So this is function phi, which is, there's two important properties that phi has. Phi is 0 on the boundary, and phi is not equal to 0 on a bounded set. And so phi can't be like 1 everywhere. It has to kind of decay at some point, and it has to be kind of concentrated in a finite or a bounded set. So these are sometimes called bump functions. And I'm going to denote this to be in this notation, c infinity, or c infinity c omega. This is kind of, they're called compactly supported smooth functions. If that makes no sense, you can just take this as notation. So, okay, if I have one of these phi, then notice that the area of the graph of u plus t phi, I can think of this as kind of a single variable function in t, and so I can differentiate it. So in particular, I can take the derivative in the direction of phi of the area at u, and this is going to be kind of d dt of 1 plus times the value of u plus t phi squared. So evaluate it, it's equal 0. So this gives us like a nice expression for the directional derivative, and then u is a critical point if this d phi area is equal to 0 for all phi. Okay, so this is great. And this is what we end up calling the graph of u. Sorry, I'm going to continue my notation. The graph of u is what's called a minimal surface. So these are kind of generalized subfilms. Okay, this is great, but is there a way to kind of phrase this in terms of the gradient of area? The answer turns out to be yes. And so there's this equation called the first variation formula, which says that if I take the directional derivative of the area at u with respect to phi, then this is actually the minus the integral of phi times the the divergence of the gradient of u over the square root of 1 plus w squared. And so if I define this guy, I'll put the minus sign inside. So it's kind of this. If you define this guy as the mean curvature h, then it turns out that so in when we're looking at functions, you can, so if I have zeta and c functions, then integrating them, or their product rather, gives me an inner product on the space of functions. And so here I can think of this as an inner product of phi with h. And so this is going to be the kind of analog of the above equation that we had with the directional derivative and the gradient, but that which allows us to think about this quote unquote mean curvature as the gradient of area. And so in general, you can define this mean curvature quantity, even if you're not like this kind of parametric form, this graph over an n-dimensional space. And if you have a surface or any sort of space with h equals 0, this is what is called a minimal surface. And so this is, I guess I'll end with this. This is kind of how we're led to thinking about minimal surfaces is as critical points of this kind of Morse-esque function. Not exactly Morse, but it's kind of the spirit, I guess, of Morse theory that brings us to this point. So I think I'll end there. If there's any questions, feel free to ask.
Yeah, thanks for a great talk. Yeah, any questions at the moment?